Namaste dear students, welcome back to physics online class. In today's class, let us derive an expression for energy stored in a capacitor. Okay, this is the last part of this particular chapter, that is one derivation important from the point of view of board exam, expression for energy stored. Now we know that a capacitor is a device which is used to store energy, electrical energy, or simply it is used to store charge. Now when charge is stored in the capacitor, what is the expression for amount of energy stored in it, that we are going to derive in this particular chapter. Now if you consider a capacitor, now this is the circuit symbol of a capacitor, any capacitor. Now let us consider the case of a parallel plate capacitor. When capacitor is uncharged, this conductor or this plate of the capacitor, the amount of charge in this plate of capacitor will be 0. At the same time, amount of charge in this plate will be 0. Totally both the plates will be electrically neutral. Okay. Now if you want to charge this capacitor must be connected to some external power supply or battery. When you connect external power supply or battery, the positive terminal of the battery removes electrons from first plate or left plate of the capacitor. As a result of this, amount of positive charge increases here. At the same time, the electrons removed from this plate are delivered to right plate of the capacitor. As a result of this, amount of negative charge increases on this plate of the capacitor. Okay. Initially, capacitor will be in uncharged condition, Q is equal to 0. When Q is equal to 0, potential difference across the capacitor will be 0 because V is directly proportional to Q. But when you connect a power supply to the capacitor, with the time, magnitude of charge increases. As a result of this, potential difference also increases. Potential difference across the capacitor also increases. And a stage reaches when the potential difference across the capacitor becomes equal to applied potential difference. V is the applied potential difference and Vc is the potential difference across the capacitor. When this condition reaches, then at that point, charging process of capacitor, transfer of charge from one plate to another, that is the charging process of capacitor, stops, and at this instant of time, amount of charge stored in the capacitor reaches its maximum possible value. Potential difference, maximum possible value, amount of charge stored is also maximum. So totally, charging a capacitor means removal of negative charges from one plate and delivering it to the other plate of the capacitor. This is how a capacitor is charged. Now, the charging process can be explained in other words like this. Charging means it is transfer of positive charge from this plate to this plate. Okay, if amount of charge stored in this plate increases by 1 coulomb, we can say that 1 coulomb of charge is shifted from negatively charged plate to positively charged plate. Like this also we can explain the charging process, shifting of positive charge from negatively charged plate to positively charged plate. Like this also we can explain the charging process. Okay, now let us try to derive the expression for energy stored in a capacitor. Let us begin with an uncharged capacitor. Okay, uncharged capacitor like this. Let C be the capacitance of the capacitor, capacity to store charge or capacitance of the capacitor. Okay, now initial point, capacitor is in uncharged condition, therefore Q is equal to 0. When Q is equal to 0, potential difference across the plates of the capacitor will be 0. So this is our starting stage, Q is equal to 0, Vc is equal to 0. With this condition, if this capacitor is connected to some external potential difference or power supply, amount of positive charge on left plate increases. At the same time, in case of right plate, amount of negative charge increases with the time. Now let us consider an intermediate stage. Okay, intermediate. After some time interval, let us consider an intermediate stage. Intermediate stage, if at this point, let amount of charge stored in the capacitor be Q dash. At that instant of time, let the potential difference between the plates of capacitor be V dash. It is not the moment when the charging process is completed. It is an intermediate stage where amount of charge is Q dash and potential difference is equal to V dash. Okay. Next, so we started from this point. After some time, we reached an intermediate stage. Again, charging of capacitor continues like this, and we will reach a final stage at which amount of charge stored in the capacitor becomes maximum. Let it be Q, capital Q. At that instant of time, potential difference across the plates of the capacitor becomes equal to potential difference connected across the capacitor. Okay, this is the final stage. So charging process started from this point and it ends at this particular point. Okay. Now, at this instant of time, that intermediate stage, the potential difference can be written as V dash is equal to Q dash divided by C. One important equation. We know that Q is equal to V into C. Now at this instant of time, Q dash is the charge and V dash is the potential difference and C is the capacitance. Therefore, we can write V dash is equal to Q dash divided by C, that is at an intermediate stage. Okay. Now what is this V dash? Okay, what is this V dash? Now this V dash is nothing but potential difference at this intermediate stage. Potential difference across the capacitor at this intermediate stage. Now the potential difference across the capacitor is nothing but it is defined as it is the amount of work done in shifting a unit positive charge from negatively charged plate to positively charged conductor. Okay, negatively charged plate to positively charged plate against the electric field. See here, electric field is directed like this, positive to negative. Okay, potential difference between the plates of capacitor at any instant of time is defined as it is the amount of work done in shifting a unit positive charge from this plate to this plate. Okay, positively charged plate to negatively charged plate. Now let us consider this point. At this instant of time, that is at intermediate stage, amount of work done in displacing a charge of magnitude, small charge of magnitude delta Q from negatively charged plate to positively charged plate. Negatively charged plate to positively charged plate, let it be delta W. So that means at this instant of time, that is in intermediate stage, if you shift a unit positive charge from here to here, in that process amount of work done is V dash. If you shift a charge of magnitude delta Q from negatively charged plate to positively charged plate, then in that process amount of work done is delta W, that is in intermediate stage. Okay, if this is the case, now just cross multiply this, you will get the relation between delta W and V dash. Now delta W is equal to V dash into delta Q. Delta W is equal to V dash into delta Q. Now what is this delta W? It is nothing but it is the amount of work done in displacing a a small charge of magnitude delta Q from negatively charged plate to positively charged plate against the electric field, that is delta W. It is equal to V dash into delta Q, or delta W can be written as now V dash is Q dash divided by C, therefore it can be written as Q dash by C into delta Q. Okay, delta W is equal to Q dash divided by C into delta Q. Amount of work done in shifting delta Q charge from negative plate to positive plate against the electric field. Okay. Now consider the first and last stage, that is initial point and final point of charging of the capacitor. Initially magnitude of charge is 0. Final point at the end of charging process, amount of charge stored is Q. That means while charging the capacitor, a total amount of charge of magnitude Q is transferred from negatively charged plate to positively charged plate. So at the end of charging process, this will be the condition. So in the charging process, external battery will transfer a charge of magnitude Q from negative plate to positive plate. Okay. So therefore, in that process, amount of work done, I'll write here, amount of work done by the external supply, it is external battery because it charges the capacitor, amount of work done in fully charging the capacitor. Charging the capacitor, that is from Q is equal to 0 to Q is equal to capital Q. If it is represented as W, then it can be written as, see, amount of work done in fully charging the capacitor from Q is equal to 0 to Q is equal to capital Q means in that entire process total amount of charge transferred from one plate to another is Q, okay, capital Q. To shift a charge of magnitude delta Q, amount of work done is this much. So to shift a charge of magnitude Q, total amount of work done is given by integral from, we started from charge of magnitude 0 with the charge magnitude is equal to 0 and the final point charge is equal to Q. So integral from 0 to Q, okay, 0 to Q into or integral of delta W. I think it is clear. For this much amount of charge, this is the work done, small charge, small amount of work done. Total amount of work done in transferring charge of magnitude Q is given by integral from 0 to Q delta W. Again, we have to use integration because that amount of work required increases with the charging of capacitor. So integral of this much. So that is equal to, let us continue the derivation, simplification, that's all. Let us continue the derivation. So that is equal to integral from 0 to Q. Now what is delta W now? Delta W is Q dash divided by C. Therefore Q dash divided by C into delta Q or simply dQ. Q dash divided by C into dQ. So that is equal to, now what is C? C is nothing but capacitance of the capacitor which is constant. It depends on the dimensions and the dielectric medium. So capacitance is constant. So take it outside. So 1 by C is constant into integral from 0 to Q, Q dash into dQ. Okay, Q dash into dQ. So that is equal to, now integrate this using this formula, integral of x to the power n into dx is equal to x to the power n plus 1 divided by n plus 1. Okay, use this formula, integral of x to the power n into dx is equal to x to the power n plus 1 divided by n plus 1. So this gives W is equal to, on integrating, W is equal to 1 by C into integral of Q dash. In the place of x we have Q dash to the power 1 it is. Therefore Q dash to the power 1 plus 1 divided by 1 plus 1 with the limits 0 to Q. Okay, with limits 0 to Q. So that is equal to 1 by C into integral of Q to the power 1 plus 1 is Q dash to the power 1 plus 1 is Q dash square divided by 2 with the limits 0 to Q is equal to W. Okay. So in the last step, substitute the limits. Okay. On substituting the limits, W is equal to 2 is, write 2 here, 1 by 2C, okay, into Q dash to the power 2 with the limit, upper limit Q. Put Q dash is equal to Q here, you will get Q square minus lower limit, that is 0. So W is equal to Q square divided by 2C. Okay. Now what is this Q square divided by 2C or W? It is the amount of work done by the external supply or battery in fully charging the capacitor from Q is equal to 0 to Q is equal to Q, that is its maximum value. Okay, that is Q square divided by 2C. Now this work done, okay, this work done is stored in the form of, stored as energy in case of capacitor. Amount of work done in charging the capacitor itself is stored as energy. Therefore, energy stored in the capacitor, energy stored in the capacitor is given by, it is represented by U. U is equal to Q square divided by 2C. Okay, Q square divided by 2C. Expression for energy stored in a capacitor, Q square divided by 2C, where Q is the amount of charge stored in the capacitor and C is its capacitance. I think it is clear. We considered charging process, initially charge as well as potential difference is 0. We considered an intermediate stage in between the charging process, Q is equal to Q dash. At that instant of time, potential difference, we considered potential difference as V dash, then that V dash can be written as Q dash divided by C using V is equal to Q divided by C formula. Now at this instant of time, we defined potential difference or general definition of potential difference. It is the work done in shifting unit positive charge from negatively charged plate to positively charged plate, and at this intermediate stage we transferred a charge of magnitude delta Q from one plate to another against the electric field with the help of a work done delta W. Next, we related these two quantities by cross multiplying this. We get delta W is equal to V dash into delta Q. Substituted the value of V dash, Q dash divided by C into delta Q is equal to delta W. In the next stage, we considered charging, complete charging or fully charging of capacitor. Charging a capacitor completely means total amount of charge is shifted. Whatever the maximum amount of charge stored in the capacitor, that is shifted from negatively charged plate to positively charged plate. Therefore, work done in that process is given by W is equal to integral from 0 to Q delta W. For this much amount of charge, this is the work done. Therefore, total transfer of total charge work done is equal to integral of this value. We substitute the values. On simplification, we got this expression, that is expression for work done, which is stored as energy. Therefore, energy stored is equal to Q square divided by 2C. Okay, expression for energy stored. I think it is clear. Important derivation from the point of view of board exam. You can expect this for 3 marks. Derive an expression for energy stored. Expression for energy stored in a capacitor. So let us consider last point, that is expression U is equal to Q square divided by 2C. Expression for energy stored in a capacitor in case of charge and capacitance in terms of charge and capacitance. One equation. Here, if you put Q is equal to V into C, we know this expression Q is equal to VC. If you put Q is equal to VC here, you will get U is equal to V square C square divided by 2C. This C cancels with this, remaining is U is equal to half into CV square. In terms of capacitance and potential difference, expression for energy stored in a capacitor, U is equal to half into CV square. Okay, half into CV square. This is the second form of equation. Okay, second form of equation. Next, again, if you modify the first equation, Q is equal to, sorry, not Q, U is equal to Q square divided by 2C it is. So I can write it as Q divided by 2 into Q divided by C. Same equation, Q square divided by 2C can be written as Q divided by 2 into Q divided by C. Now this becomes U is equal to Q divided by 2, it remains as it is, Q divided by 2, Q by C. Now Q is equal to VC, therefore Q divided by C means it is equal to V, therefore this term is equal to V, therefore it becomes QV divided by 2. This is the third form of equation. Okay. So 3 equations, Q square divided by 2C, that is in terms of charge and capacitance, U is equal to half CV square in terms of capacitance and potential difference, and QV divided by 2, that is in terms of charge and potential difference across capacitor. So 3 different expressions for energy stored in a capacitor, important equations. Okay, next, if you consider a parallel plate capacitor, which we discussed in earlier videos, parallel plate capacitor. In case of parallel plate capacitor, capacitance is given by epsilon naught A divided by D. At the same time, electric field between the plates of capacitor is given by E is equal to sigma divided by epsilon naught. Okay, sigma divided by epsilon naught. Now consider this equation. Energy stored U is equal to Q square divided by 2C. Q square divided by 2C. Now this can be written as one more equation is there, that is magnitude of charge stored in the capacitor can be written as sigma into A. Charge density is charge per area. Q divided by A is sigma, therefore Q can be written as sigma into A. So now this equation can be written as Q is sigma into A square divided by 2 into C, 2 into 1 by C it is. C is epsilon naught A divided by D. Therefore, 1 by C is D divided by epsilon naught A. I think it is clear. Q is sigma A, Q square. 1 by C is there. C is epsilon naught A divided by D. Therefore, it is 1 by C is D divided by epsilon naught. So, this is equal to from this sigma can be written as epsilon naught into E. Sigma is epsilon naught into E. Therefore, this equation becomes is equal to sigma is epsilon naught into E square, sigma square into A square into D divided by 2 times epsilon naught into A. Sigma is epsilon naught E square into A square into D divided by 2 epsilon naught A. Now this A cancels. Epsilon naught cancels here. 1 epsilon naught cancels. Remaining terms are 1 by 2. Epsilon naught square, epsilon naught cancelled. So remaining is epsilon naught. E square is there. E square into A into D. So U. Expression for energy stored in a parallel plate capacitor in terms of electric field and dimension, that is area of each plate and separation between the plates. Half into epsilon naught into E square into A into D, that is the expression for energy stored in a parallel plate capacitor. Next, one more expression, energy stored per unit volume. Energy stored per unit volume of parallel plate capacitor. Energy stored per unit volume is, let it be some U dash. Okay, energy stored per unit volume is equal to total energy stored is U, per volume means divide that U by volume, U divided by volume. It is not potential difference, it is volume. Okay, divided by volume is equal to half into epsilon naught E square A into D, epsilon naught E square into A into D divided by volume of the capacitor. Volume of the capacitor is area into separation between the plates. If this is the capacitor, volume of this region is area of each plate of the capacitor multiplied by some separation between the plates, that gives volume. So divided by A into D. This AD cancels. So energy stored per unit volume U dash is equal to half into epsilon naught E square. Energy stored per unit volume of the capacitor. Important equations: energy stored per unit volume, energy stored in a parallel plate capacitor, and different expressions for energy stored in a capacitor. Okay, I think it is clear. So this completes theory part. Okay, theory part, that is capacitors and capacitance. Let us solve few problems based on this concept, that is energy stored in a capacitor and also combination of capacitors. Few problems are remaining. Let us solve that. Okay. Yes. Next problem. Two condensers, condenser means capacitor, of capacity 5 microfarad and 10 microfarad are charged to 16 volt and 13 volt respectively. What is the common potential when they are connected in parallel? See, it is the problem containing two capacitors. Let C1 be the capacitance of first capacitor, it is equal to 5 microfarad. Capacitance of second capacitor is C2 is equal to 10 microfarad. Now given that these two capacitors are charged separately, first of all the capacitor 1 is connected to a battery, okay, a potential difference of V1 is equal to potential difference applied to first capacitor is 16 volt. Okay, it is charged to 16 volt, and the capacitor C2 is charged to a potential difference of 13 volt. So now it is connected to, or it is charged to 16 volt. Capacitor C1 is charged to 16 volt, and then another capacitor C2 it is charged to 13 volt. This is charged to 16 volt. Now when these two are, after charging the capacitors separately, if these two are connected in parallel, okay, parallel combination, if these two are connected in parallel, now what is the potential difference across the combination? Before connecting the capacitors in parallel, 16 volt is the potential difference of first, 13 volt is the potential difference of second. If you connect these two in parallel, what is the new potential difference? That is the question. Okay. Now, we know that Q is equal to V into C. Q is equal to V into C. Now, using this, charge stored in first capacitor Q1 is equal to V1 into C1 is equal to, Q1 is equal to V1 into C1 is equal to 5 into 10 to the power minus 6 into potential difference is 16. If you multiply this, Q1 is equal to 80 into 10 to the power minus 6 coulomb. Charge stored in first capacitor. Similarly, charge stored in second capacitor Q is equal to V2 into C2 is equal to 10 microfarad, that is 10 into 10 to the power minus 6 capacitance into potential difference is 13 volt, isn't it? 13 volt. So now this is equal to 10 into 13, 130 micro, 130 into 10 to the power minus 6 coulomb. Okay. Now these two are connected in parallel. Okay. When these two are connected in parallel, total charge stored in parallel combination, okay, total charge stored in parallel combination, Q is equal to, we know that Q1 plus Q2. Total charge stored is equal to Q1 plus Q2, that is equal to 80 into 10 to the power minus 6 plus 130 into 10 to the power minus 6. Therefore, Q is equal to 210 into 10 to the power minus 6 coulomb. Amount of charge stored. Okay, amount of charge stored. So therefore, okay, so this is the total amount of charge. Now capacitance, when these two are connected in parallel, capacitance of the combination, total capacitance of the combination, parallel combination it is, therefore it is C1 plus C2. So Cp is equal to C1 plus C2 is equal to, first one is 5 microfarad plus 10 microfarad, total it is 15 microfarad. So Cp is equal to 15 microfarad. So we connected these two in parallel, these two capacitors in parallel. Total amount of charge stored in this combination is equal to 210 into 10 to the power minus 6 coulomb. And if you consider the effective capacitance of these two, that is equal to 15 microfarad. So amount of charge stored Q is equal to 210 microcoulomb, and total capacitance Cp is equal to 15 microfarad, 15 microfarad. So therefore, now what is the potential difference now? We want to calculate the potential difference. We know the value of capacitance, we know the value of total amount of charge stored. Okay, total amount of charge stored. If this is the case, what is the capacitance, sorry, what is the potential difference? So therefore, last step, therefore, potential difference across parallel combination. Potential difference across parallel combination, V is equal to total charge Q, because total charge in that combination divided by effective capacitance Cp is equal to 130 into 10 to the power, sorry, not 130, 210 into 10 to the power minus 6 divided by Cp value is 15 into 10 to the power minus 6. So 10 to the power minus 6, 10 to the power minus 6 cancels. So 210 divided by 15 is 6. Sorry, not 6, 1, 14 volt. So V is equal to 14 volts. So when two capacitors are charged separately, then those two capacitors, if connected in parallel, what is the total potential difference across the combination? To find the total potential difference, first to calculate the amount of charge stored in each capacitor, then find the total amount of charge, then find the effective capacitance of the combination. Then if you divide this amount of charge by capacitance, you will get the common potential difference. It is called common potential difference between the combination. Okay. Now you can solve this. If it is asked in theory exam, you have to solve it like this only. You have to follow all these steps. If it is asked in competitive exams, then you can use a shortcut formula. See, two capacitors, C1 charged to V1, another capacitor C2 charged to V2. If these are connected in parallel, okay, if these are connected in parallel, after charging these are connected in parallel with the positive plate of one capacitor connected to positive plate of other, negative plate to negative plate, under that condition, after connecting these two, what is the common potential difference? It is given by the formula V is equal to V1 C1 plus V2 C2 divided by C1 plus C2. So in competitive exams, to calculate the potential difference across the combination, you can use this formula V1 C1 plus V2 C2. If the same two capacitors, now this is C1 and this is C2, if the same two capacitors are connected in parallel like this, another possibility, just concentrate on the connections. If positive plate of one is connected to negative plate of other, here also negative plate to positive plate. Here positive to positive. Positive plates are connected together, negative plates are connected together. This is the formula. If positive of one is connected to negative plate of other, then common potential difference across the combination in this case, potential difference across the combination in this case is given by V is equal to V1 C1 difference V2 C2 divided by C1 plus C2 instead of plus difference. Okay, difference. So this is when capacitors are connected in parallel like this. For normal parallel connection, this is the shortcut formula to calculate the common potential difference. So you can use, using this formula, you can calculate common potential difference in this particular problem. Okay, I think it is clear. Let us move on to next problem. A capacitor of 4 microfarad is connected to a 400 volt battery. It is then disconnected and connected to an uncharged capacitor of 2 microfarad. Calculate the common potential difference. Again, similar problem. Okay, similar problem. I'll just explain the problem. You can solve by yourself. See, capacitor of capacitance C1 is equal to 4 microfarad. Now this capacitor is charged to a potential difference V1 of 400 volt. Okay, 400 volt. Second capacitor of capacitance C2, its capacitance is 2 microfarad, but it is given that it is connected to an uncharged capacitor. Uncharged capacitor means the potential difference across the second capacitor is equal to 0. First capacitor is charged, second capacitor is uncharged. Now these two capacitors are connected like this, connected in parallel. So what happens in this case? This is charged, this will have certain amount of charge on it. This is uncharged, total charge is 0 in this case. So when these two are connected in parallel, charge will flow from this capacitor to other. So this capacitor gets charged and this capacitor gets discharged. Okay, so here a common potential difference is created, common potential difference across the combination. Now what is the value of that common potential difference? Okay, common potential difference. Solve the problem using the steps we followed in the previous problem. At the same time, you can solve the same using V1 C1 plus V2 C2 divided by C1 plus C2 formula. Using this formula also, you can solve the problem. Okay, so complete it yourself. So the next problem is, two batteries 65 volt and 45 volt are connected to two capacitors of capacitances 25 microfarad and 35 microfarad respectively. So first capacitance C1 is equal to 25 microfarad. Second capacitance C2 is equal to 35 microfarad. So it is connected. First capacitor is connected to 65 volt battery. Second capacitor is connected to 45 volt battery. Okay, 45 volt battery. Now using this information, or before that, then they are connected in parallel. After removing the battery, the capacitors are connected in parallel. Calculate the energy stored in individual capacitors. That means what is the amount of energy stored in first capacitor and the second capacitor, then energy stored in the combination. After combining those, connecting those two capacitors in parallel, what is the amount of charge, energy stored, and lastly, what is the amount of energy dissipated? Okay, what is the amount of energy dissipated? These things you have to calculate. A lengthy problem. Let us start with calculating the charge stored. Now Q1, amount of charge stored in first capacitor, can be calculated as Q1 is equal to V1 into C1. Substitute the values, 25 into 10 power minus 6 into 65. So you will get 25 into 65. So 25 into 65 is equal to 1625 into 10 to the power minus 6 coulomb. Similarly, charge stored in second, Q2 is equal to V2 into C2. V2 is 45. Okay, 45 into 35 into 10 to the power minus 6. So 45 into 35 is equal to 1575 into 10 to the power minus 6 coulomb. This is the amount of charge stored in these two capacitors. Now energy stored in first capacitor, let it be U1. Now this is energy stored before connecting them in parallel. Energy stored in first capacitor U1 is equal to, we can use any formula, half into CV square. I will use half into CV square formula, or you can use Q square divided by 2C also. If you use Q square divided by 2C, what you will get? Q is, so Q1 divided by Q1 square divided by 2C1. Q1 is 1625. So 1625 into 10 power minus 6 square divided by 2 into 25 into 10 power minus 6. So is equal to 1625 into 1625 square divided by 2 into 25, that is 50. So it is equal to 52812 into 10 power minus 6 square means minus 12. So that 1 10 to the power minus 6, 1 10 to the power minus 6 cancels. So remaining will be 10 power minus 6 joule energy stored in first capacitor. Similarly, energy stored in second capacitor U2 is equal to Q2 square divided by 2C is equal to 1575 square into 10 to the power minus 6 square divided by 2 into, so it is 2 into 35 into 10 power minus 6 is equal to 1575 square divided by 2 into 35 is 70, okay, 70. So it is 35,437 into 10 to the power minus 6. Again 10 power minus 6, 1 10 to the power minus 6 cancels with this much amount of joule. Okay, that is energy stored in second capacitor. Okay, second capacitor. Therefore, total energy stored before connecting in parallel, total energy. So before connecting in parallel, total energy Ui is equal to U1 plus U2 is equal to, add these two values, 35,437.5 plus 52,812 88,249. 88,249 into 10 power minus 6 joule is the total energy stored. Okay. Now, these two capacitors are connected in parallel. So, capacitors are then connected in parallel. That is the condition given. The capacitors are then connected in parallel. So, after connecting the capacitors in parallel, total charge stored. After connecting the capacitors in parallel, total charge stored in the combination QP, I'll write it as QP, is equal to Q1 plus Q2 because these two are connected in parallel. Okay, total charge. So that is equal to, charge in first is 1625. So 1625 plus 1575 into 10 power minus 6 is there. If you add these two values, you'll get 0, 0, 12, 3,200, right? 3,200 into 10 to the power minus 6 coulomb. This is the charge. And also capacitance, since these are connected in parallel, capacitance Cp is equal to C1 plus C2. We know the formula for capacitance in parallel. So it is equal to 25 plus 35 into 10 to the power minus 6 is common, that is equal to 60 into 10 to the power minus 6 farad capacitance. Okay. So therefore, last part, therefore, after connecting in parallel, energy stored. After connecting in parallel, energy stored in the capacitor, I'll represent it as UF is equal to Q square divided by 2C, that is 2Cp. Substitute the values. Total charge is 3,200 into 10 to the power minus 6, it's a square, Q square divided by 2 into 60 into 10 to the power minus 6. So that is equal to 3,200 divided by 120. So you will get 85,333.3 into 10 power minus 6 square, 10 power minus 6, 1 10 power minus 6 cancels, 10 power minus 6 joule. This is the amount of energy stored. So before connecting the capacitors in parallel, this is the amount of energy stored, and after connecting the capacitors in parallel, this is the energy stored. Now if you compare the values, it is 88,249 into 10 power minus 6, its value is 85,000. So after connecting the capacitors in parallel, amount of energy stored in the combination decreases. That is, energy is dissipated. This energy is dissipated in the connecting wires. See, when capacitors are separate, energy stored is this much amount. When these two are connected in parallel using conductors or conducting wires, certain amount of energy is wasted, that is dissipated in the form of heat energy in this part of the circuit, that is in case of wires. Okay, so therefore energy dissipated, last part. Okay, when capacitors are connected in parallel, energy dissipated, amount of energy dissipated is equal to initial energy stored minus final energy is equal to 88,249 into 10 power minus 6 minus 85,333.3 into 10 power minus 6. So it is equal to the difference. 88,249 minus 85,333.33 is equal to 2,915.6 into 10 to the power minus 6 joule. Okay, so this much amount of energy is lost when two charged capacitors are connected in parallel, and energy dissipation takes place in case of connecting wires. Electrical energy is converted into heat energy, and that much amount of energy is lost. This is the amount of energy dissipated. Okay, now this is how you have to calculate the energy dissipated when two charged capacitors are connected in parallel.